Here we have a typical question involving exponential decay. We'll read the question first. One of the main radioactive elements released from nuclear disasters is strontium-90. We'll call that S90. If the amount of S90 present at time t is given by S of t, like a function involving t, the decay of S90 is given by S of t equals S0 e to the minus 0.025 t. So we've got our exponential models involving e to the minus kt. So we have k as a factor of negative 0.025, into the negative sign indicating we have decay going on. The amount present is getting less and less and less. T is measured in years. S0 is the initial amount of S0, of strontium-90, beg your pardon. Estimate the half-life. What do we mean by half-life? So if S0 is present initially, then we want to find out when we get exactly half of that. Half of that is 0.5 S0. And we want to find out the time that elapses. That's what we're trying to find, the time that it takes to go from an initial amount to half the initial amount. So we've got S of t, our amount present, equals S0 e to the minus 0.025 t. Now that will tell us the amount that's present at any time, given that S0 is the amount present when t equals 0. So we want to find out what is the value of t when S0 is equal to that. So we've got 0.5 S0 equals S0 e to the minus 0.025 t. We don't need to know how much was present in when t equals 0, or the initial condition. So S0, as you can see, if we divide both sides by S0, we get 0.5 equals e to the minus 0.025 t. Now we're trying to estimate t, or trying to find t, which will be the half-life. We know what e is. And as we've seen in previous work done, that when the unknown is in the power, a common way to solve is to take logs of both sides. Now, because we've got e to a power, we'll take logs to base e. So take natural logs, both sides. Natural logs is log to base e. Another way to write it, both mean the same thing. So we're going to take log, natural log 0.5 equals natural log of e to the minus 0.025 t. Now we've already seen that when we've got log of something to a power, one of our properties said that the power can come out the front. So negative 0.025 t ln of e equals, this side does not change. The log of e, the log to base e of e, don't forget log is a power. So you're saying, what is the power I must raise e to get the number e? Well, I must raise e to the power of 1 to get e. So that is simply equal to 1. So therefore we've just got a single equation now, an easy equation to solve. We want t by itself, so we divide both sides by negative 0.025 t. So we got t equals ln 0.5 all over negative 0.025. And when we do that on our calculator, so be very careful, we've got ln divided by, depending on your calculator, you may need to put brackets around this here with the negative sign there, and we'll get 27.7. And t was measured in years. So basically what's that saying is that it takes 27.7 years for the amount to decay to get half of the initial amount. Let's just have a look at what that would look like on a graph. So here's my t-axis and here's my s. Now s, or s of t, is the amount that's present. Now we know that the initial amount present was S0, and then after that it decayed away. So that's what our exponential graph looks like when the power is a negative. In this case it is, so we get decay. Now what does it mean? That means that when half of this, so if we go up 1, 2, 3, 4, we've gone up 4 units on our graph here. So here's my half of S0, and that's my time that I've, the half-life. So this is 27.7. We've gone from S0 to a half S0. Now, what's half of that? Half of this is a quarter S0. Now, that's down to here. So that should be the same. And if we go out to here, if I've drawn it, that's also 27.7 years. And likewise, if I half that and go out again, if I'd drawn it accurately, that's also 27.7, and so on. So we could continue out there and it would go indefinitely. So this is also 27.7. Maybe the graph's not too accurate there, but you can get the idea that this is what's meant by half-life. You could have started anywhere here and find out how long it takes to get to half of that, and you would still get the 27.7 years. So we've actually just used S0 as our initial amount. So this is a very typical question with radioactive decay. It's an exponential decay question. We need to be able to take logs of both sides. It's once again a typical type of way of solving equations when you've got the unknown as a power.